End of class. Today we're going to talk about L'Hopital's rule. This is one guy's name. I'm not even going to try to say it. He was a French mathematician. Continue. Yeah. And, yeah. So he was a French mathematician. He wrote the first European textbook on calculus. Quotes around the word wrote because virtually the entire textbook was lifted directly from notes made by another mathematician named Bernoulli. L'Hopital had paid Bernoulli to tutor him in calculus because he was one of only a handful of people in the world who understood this new subject. And Bernoulli sent L'Hopital a bunch of notes on calculus, and then L'Hopital published them as a book that he called his own. So today we are going to study a rule named after him that is probably not really his. Okay, so we're going to take a look at a couple of limits here. We're going to do each problem in two ways. All right, so the limit as x approaches 2 of 3x squared minus x minus 10 over 5x squared plus 3x minus 26. Now what happens if I just try to plug in the 2? You get 0 over 0, yeah, so 2 squared is 4, minus times 3 is 12, minus 2 is 10, minus 10 is 0. So if we just plug in the 2, we get 0 over 0, which is an indeterminate form, right? We cannot tell what this is going to go to. So when we get an indeterminate form, remember, that just means you have some more algebra to do. You have to try to simplify this thing. So maybe we can factor and cancel something. So let's see, 3x let's see, factors of 10, 5 and 2. If I put a 2 here and a 5 here, I think that works. 3x squared, 6x, and 5x. So I want minus 6x plus 5x to get the minus x. All right, and then I'm hoping there's going to be a minus 2 down here. So that helps me work through my factoring. So this is this would have to be a 13, and it would have to be a plus. Yep, that works. Okay, so that means I can factor my x minus 2's. Cancel my x minus 2's. And now when I plug in a 2, I get 6 plus 5 is 11 over 10 plus 13 is 23. All right, so how else could I have approached this problem? Like, let's say you tried to factor it and cancel it, and you just couldn't figure out the factoring. The quotient rule is only for a derivative, right? A limit is something different than a derivative, yeah. Yeah, we're thinking way back here. I suppose we could have figured out how to factor it by, we could have graphed it, found a 0, done long division, found another factor. I want to do that. But yeah, you could have figured out how to factor it that way. I'm looking for the word numerically here. So I want to, in y equals, I'm going to put the function that I'm trying to take the limit of, 3x squared minus x minus 10 divided by 5x squared plus 3x minus 26. And then go to my table. Oh, thank you. All right, so now I'm going to go to my table, and I want to plug in values as x gets closer and closer to 2. So I could plug in like 1.9, 1.99, 1.999, things like that. Or 2.1 to approach from the other side, 2.01, 2.001. The problem with this numerical approach is that I'm going to get an approximation. Right? You can't always guess exactly what the limit is. I wouldn't look at those decimals and go, oh, it's approaching 11/23. I don't know, you might, but I don't see that. So we like the algebraic approach better for this reason, that you can get a more exact answer. But you can't always factor and cancel. All right, let's look at same function, right? 3x squared minus x minus 10 over 5x squared plus 3x minus 26. But this time I'm looking at the limit as x goes to infinity. So you can't plug infinity in, right? You have to just think about what happens as you plug in bigger and bigger numbers. So the limit as x goes to infinity is the end behavior of this rational function. Anybody remember a rule for how to do that? Yeah. We can just look at the leading terms of the top and the bottom, because if we're going towards infinity, right? Think about the largest number you can conceive of, like a gajillion, a ginormous number. Plug that in for x into the top and the bottom here. A gajillion squared is a gajillion times a gajillion, which is a gajillion times bigger than a gajillion. It's so much bigger that we can't, that a gajillion just gets dwarfed. So the limit as x goes to infinity of this function is the same thing as the limit as x goes to infinity of just 3x squared over 5x squared. Because all the other terms are just so small in comparison that they hardly make a difference. And then I can cancel my x squareds. So this is the limit as x goes to infinity of 3/5, which is just 3/5. It's a constant. And again, we could have done this numerically. So we did this sort of by reasoning, not really algebraically, but by reasoning through. And now I can do it numerically, where I plug in larger and larger values for x. So I could start with like 10, 100, 1,000, 10,000. That was 100,000. And I could maybe 1,000,000. And it does look like I'm approaching 0.6, which is the same as 3/5. Okay, so those are two ways that we already knew how to do these. I'm going to go back and do them again using a new technique. Okay, so if I want the limit as x goes to 2 of 3x squared minus x minus 10 over 5x squared plus 3x minus 26, you get 0 over 0, right? So the question is, does the numerator or the denominator go to 0 faster, right? If the denominator goes to 0 faster than the numerator, then the denominator is going to shrink, making the fraction blow up, right? And if the numerator goes to 0 faster than the denominator, the numerator will shrink and it'll make the whole fraction go to 0. But they also could kind of like fight and balance each other out at some point. So that's why it's indeterminate. It's the speed at which the numerator and denominator go to 0 that tells us what's going to happen. So how can you determine the rate of change of a function Its derivative, yeah. So we can use the derivative as the rate of change. So I can say, well, the limit as x approaches 2 of 3x squared minus x minus 10 over 5x squared plus 3x minus 26. I'm going to take the derivative of the top and the bottom, not the quotient rule, but the derivative of the top and the derivative of the bottom. So I get 6x minus 1 over 10x plus 3. And now what happens when I plug a 2 in? (11/23), which is what I got when I did factor and cancel and by a numerical technique. All right, let's see if the same technique works down here. The limit as x approaches infinity, 3x squared minus x minus 10 over 5x squared plus 3x minus 26. Well, the question is, how fast does the numerator go to infinity? How fast does the denominator go to infinity? If the denominator goes to infinity fastest, then this fraction will go to 0, because the denominator is going to shrink down faster than the numerator, making the fraction bigger. If the numerator goes to infinity fastest, then the fraction will blow up. But they could struggle and meet in the middle somewhere. So the way I find the rate, how fast each of these is changing, is the derivative. So I take the limit as x goes to infinity of 6x minus 1 over 10x plus 3. They're still both going to infinity. They're both lines that are going to grow to infinity. So I can do it again. Take the derivative of the top and the bottom again, and I get the limit as x goes to infinity of 6/10, which is 3/5. Same thing I got just thinking it through or using a numerical technique. So this technique works for any limit of an indeterminate form, which is 0/0 or infinity over infinity. And the technique is called L'Hopital's rule. Okay, so here it is, just written out formally. It says if you want to take the limit of a fraction, right, like the limit as x goes to a of f over g, but the numerator and denominator both go to 0, then that is the same thing as the limit as x goes to a of f prime over g prime. And the same thing, if the top and bottom both go to infinity, you can do the derivative of the top and the bottom also. Yep, you can do it more than once, yep. All right, we're going to do several of these now. We'll work on the remainder after we finish the new material today. You have to justify your use of L'Hopital's rule before you use it. You have to show that it goes to 0/0 or infinity over infinity, because that's the only time that it applies. Okay, so also, L'Hopital's rule says differentiate the numerator and denominator separately. You do not use the quotient rule here. We're not taking a derivative of the function. You're taking the derivative of the top over the derivative of the bottom. Okay, so what happens in A here if I plug the 2 right in? Zero over 0. 2 squared is 4, minus 4 is 0, 2 minus 2 is 0. Okay, so it's an indeterminate form. I can apply L'Hopital's rule. I also could factor and cancel this, right? But we're practicing L'Hopital's rule now, so. So that L'Hopital's rule says I can take the derivative of the numerator and the denominator. So the derivative of my numerator is 2x, derivative of the denominator is 1. Now what happens when you plug in a 2? You get 4. There's our limit. All right, the limit as x goes to 0 of sine of 2x over x. What's the sine of 0? 0. And when I put a 0 in the denominator, I get 0. 0 over 0. Okay, so now I can use L'Hopital's rule to evaluate this limit by taking the derivative of the top and the bottom. What's the derivative of sine 2x? 2 cosine 2x. Now when I plug a 0 in there, what's the cosine of 0? 1. So this says 2 times 1 over 1 is 2. All right, let's jump down to D here. All right, if I plug a 2 in here, what do I get? Is that 0 over 0 or infinity over infinity? No, in fact, it's just a number, right? So I'm done. No need to use L'Hopital's rule. This is why you have to check. Just because we're in the L'Hopital's rule section doesn't mean you always have to use L'Hopital's rule. All right, let's look at I. The limit as x goes to infinity of x over e to the x. What happens to the numerator and the denominator here as x goes to infinity? They both go to infinity. Okay, so that is a case where I can apply L'Hopital's rule. So this is going to be the limit as x approaches infinity of 1 over e to the x. Derivative of x is 1, and the derivative of e to the x is e to the x. So now what happens as x goes to infinity? Yeah, my numerator stays 1, and my denominator is going to get huge, so the whole fraction is going to go to 0. All right, and J. Limit as x goes to 0 from the right of ln x over cosecant x. All right, what's the ln of 0? Doesn't exist, right? Well, what's the limit as you get close to 0 from the right? So here's a graph of ln. This might help. As I'm approaching 0 from the right, what's happening to my y values of ln? Negative, yeah, negative infinity. My numerator is going to approach negative infinity. And then cosecant of 0. Well, cosecant is the reciprocal of sine, right? What's the sine of 0? 0. What's the reciprocal of 0? Think of 0 as 0 over 1. What's its reciprocal? Undefined, yeah, 1 over 0. But now instead of thinking of it as 0, thinking of it as approaching 0. Infinity. Yeah, 1 over something getting really, really small goes to infinity. And if you had no idea about how to think about those limits, just put them in your calculator and get a numerical. You would pretty quickly see that they're going to infinity, negative infinity, infinity. So the negative sign is okay. We are allowed to use L'Hopital's rule with a negative sign in there. So this says the limit as x approaches 0 from the right, I can take the derivative of the top, which is 1 over x, divided by the derivative of cosecant x. Have it off the top of your head? All right, let's derive it. Come on. There we go. All right, I want d dx of cosecant x Yep, this is d dx of 1 over sine x. I could use a quotient rule, right? I'm going to have some zeros pop up because my numerator is a constant. Or I could write this as d dx of sine x to the negative 1 and use the power rule. You can do whichever one you like. I'm going to do the power rule here, so I get negative sine x to the negative 2, but then multiply by the derivative of the inside function, which is cosine x. So this ends up as negative cosine x over sine squared x, which is negative cosine x over sine x times 1 over sine x. And what's cosine over sine? Cotangent. So this is negative cotangent x. What's 1 over sine? Cosecant. All right, there's my derivative. Negative cotangent cosecant. All right, now we got to approach 0 from the right. All right, so what's happening to my numerator as x goes to 0? 1 over x as x goes to 0. Yeah, it's getting smaller. No, x is getting smaller. What's happening to 1 over x? It's getting larger. It's going to infinity. All right, what's the cotangent of 0? Cotangent is cosine over sine. Cosine of 0 is 1. So that's going to go to infinity. And cosecant is 1 over sine, also going to go to infinity, right? Yeah. Okay, I could do it again. Or I could just do a little algebraic manipulation here. And instead of putting 1 over x on the top, I can do 1 over and put the x in the bottom. Oh, that's not going to help me though, is it? Because now x is going to 0, but the cotangent and cosecant are going to infinity. And what's 0 times infinity? Which one wins, right? So that doesn't help, so I think I have to do it again. Ooh. Okay, so what do you get when you multiply something super close to 0 by something super close to infinity? It depends. How close are you to 0 and how close are you to infinity? It depends. So here, if I'm going to approach 0 from the right, I have x times 1 over x. Well, that x is going to go to 0, and 1 over x is going to go to what? Infinity. So multiplying something really close to 0 with something really close to infinity. But I can simplify. X times 1 over x is 1. So the limit as x approaches 0 from the right of x times 1 over x is just 1. Because I could just simplify x times 1 over x. Okay. So this would be a simplify x times 1 over x to a 1. So the limit is 1. So sometimes when you multiply 0 times infinity, you get 1. Let's look at another example. Again, I'm going to approach 0 from the right. This time x squared times 1 over x. X squared is going to approach 0. 1 over x is going to approach infinity. So we're doing 0 times infinity, or something close to 0 times something close to infinity. But this limit, I could simplify. X squared times 1 over x simplifies to x. So what's the limit as x goes to 0 from the right of x? 0. So sometimes when you multiply something close to 0 by something close to infinity, you get 0. Sometimes you get 1. Let's get one more example. Square root of x times 1 over x. The square root of x goes to 0. 1 over x goes to infinity. But again, you can simplify the argument, the thing we're taking the limit of. This would be x to the 1/2 over x to the 1, which simplifies to 1 over x to the 1/2. And what happens to that fraction as x goes to 0? Goes to infinity, because the square root is an increasing function, so the denominator is getting bigger and bigger, smaller and smaller and smaller, and so the fraction is going to infinity. So you get 1, you get 0, you get infinity, you can get and many other things too. So this is an indeterminate form, 0 times infinity, just like 0 over 0. We don't know what the answer is. Also, infinity minus infinity, indeterminate form. Because think about how many counting numbers are there? 1, 2, 3, 4, 5, 6, 7, 8. How many are there? Infinity. How many even counting numbers are there? Infinity. So what is infinity minus infinity in that case? Counting numbers minus even counting numbers. Infinity still, right? You have infinity left over. You have all the odds. So you might think that this should be 0, but it could be also infinity. It could be any number in between, depending on the sets we're looking at. 0 to the 0, infinity to the 0, and 1 to the infinity, all indeterminate forms. So in each of these cases, in all 5 of those indeterminate forms, the way that we deal with this is that we have competing forces, and you can write all of those 5 indeterminate forms by doing some fancy algebra. You can always rewrite it as a fraction that will look like 0 over 0 or infinity over infinity. Now these guys don't have competing forces, so L'Hopital's rule doesn't apply. 0 over infinity, right? If your numerator is going to 0, that makes your fraction go to 0. And if your denominator is going to infinity, that also makes your fraction go to 0. So there's no competition there. They're working together to make the fraction go to 0. Infinity over 0, right? If your numerator is going to infinity, that makes your fraction go to infinity. And if your denominator is going to 0, that also makes your fraction go to infinity. So again, those are cooperating. They're both forcing the fraction to go to infinity. Same with 1 to the 0, 0 to the 1, and 0 to the infinity. They are not competing forces, right? 1 to the 0 would be 1, 0 to the 1 would be 0, and 0 to the infinity would be 0. So the only indeterminate forms that you are going to be responsible for are 0 over 0, infinity over infinity, which we've already looked at, those two, and 0 times infinity. So for 0 times infinity, we just have to try to rewrite it so that we can make it look like 0 over 0 or infinity over infinity. So let's look at part A here. X ln x, limit as x goes to 0 from the right. So what happens as x goes to 0? X approaches 0, and what happens to ln x? Goes to negative infinity, yeah. All right, so we've got 0 times negative infinity. All right, so you can't apply L'Hopital's rule until we make it look like 0 over 0 or infinity over infinity. So I'm just going to do a little trick of algebra. I already have an infinity, right? So if I leave my ln, leave my ln x in the numerator, leave my ln x in the numerator, and I'm going to move my x to the denominator, right? But if multiplying by x would be the same as dividing by what? 1 over x, yeah. So just a little algebraic manipulation, right? So almost always when you learned about how to manipulate negative exponents, we're supposed to rewrite the problem with no negative exponents. Now we're introducing one, right? So now I have an x to the first in the numerator. To move it to the denominator has to be an x to the negative 1, right? Which is the same as 1 over x. So this is the limit as x goes to 0 from the right of ln x divided by 1 over x. And now ln x goes to negative infinity. 1 over x as x goes to 0 goes to infinity. So now it's of the form infinity over infinity, and we can apply L'Hopital's rule. Okay, so I take the derivative of my numerator, which is 1 over x, the derivative of my denominator, which is negative 1 over x squared. Still infinity over infinity, but I can simplify that expression a lot. So this is the limit as x goes to 0 from the right, 1 over x times the reciprocal of the denominator, and then we'll cancel. So I end up with negative x. And as x goes to 0, negative x goes to 0. Okay, I'm going to skip B because, like I said, you're not going to be tested on that technique, and I want to make sure we leave plenty of time for this quiz. So I think I will also skip this and move on to the quiz.